All right, so welcome back. Talk about reflexes and some reflex arcs. So we all know what a reflex is, right? I mean, so here's a definition. You can read it on the screen, right? It's a fast, predictable, automatic response to a change in the environment, right? That helps maintain homeostasis. So you know what a reflex is, right? So like we had mentioned one earlier in the lecture, like you hold on, like you grab a hot pot, your immediate response without even thinking is to like let go, right? It's very predictable. Every single time you're gonna let go as a reflex, right? Unless, like, again, you had that example of you're going to drop it on a baby's head or something, you probably will move it. You'll have a different response, whatever. The point being is your reflexes they're fast, they're predictable, and they're automatic, right? You don't think about it, you just do it, right? If someone comes up and even like scares you, you go, whoa, you startle, that's a reflex, okay? Or if someone throws something at you, you move, it's a reflex, right? You step on something sharp, you're gonna you automatically pick up your foot. You don't go, that's sharp, ooh, and painful. Should I pick up my foot? No, you just do it, right? There's no thought process other than who left the tack on the floor. I'm gonna kill you. All right. Anyway, so depending on where they are, they can be spinal, meaning they just go to the spinal cord and back out. So these are the really fast ones. They can be cranial, and most of these do have a cranial component to them. So basically that means that there's a signal that goes up to your brain. So you drop in the pot, it's hot. Like a second later, like you've actually dropped it already, or in the process of dropping it, and then the brain registers it as hot, right? They're somatic, meaning, again, they're like dealing with muscles and muscle reactions. Or sometimes they're autonomic. So these are things we're not really gonna touch on these, but autonomic ones would be like if you flash a light in someone's eyes, their pupils will constrict. That's a reflex. You turn lights off, the pupils will dilate. This is not stuff that you necessarily think about. Okay. All right. So let me see if I can either move me or hide me. Nope, I'm gonna hide me. All right. So a reflex arc has 5 different components. So you have the receptor. Again, like the pain one, you have to actually feel it. If you're not feeling it or you're not picking up on it, you can't respond to it, right? So the first thing is going to respond to a stimulus, right? Then the second part is going to be the actual neuron, right? So from the receptor, it's taking it to what's known as that integration center. And that integration center, you have to get that sensory information and you got to turn it into a motor output. Excuse me, so that's what that integrating center is going to do. It's going to take that sensory information and give that to the motor neuron so they can actually do something with it. So then the motor neuron takes that motor information to a muscle or sometimes a gland, and then you're going to move your hand or you're going to let go of the pot or you're going to step off the tack, right? So that's basically how it works. We have some very simple ones. Sometimes they only have one synapse. We'll see there's a few that have a little bit more. Okay. So again, the reason why these are so helpful is that they allow you to respond to something very quickly to minimize any kind of damage. Again, by the time you're registering that the pot was hot, you've already are in the process of letting go of it. So even that milliseconds will give you will prevent that much more damage to your skin, right? For example. All right, so we're going to take a look at 3 different ones. So there's something called the stretch reflex, the tendon reflex. Actually, we'll take a look at 4. The stretch reflex, tendon reflex, this one should be a separate one. The flexor withdrawal reflex, and then the crossed extensor reflex. So there's 4. That just didn't get its own bullet point for some reason. All right, so before we get into the very first one of the things I want to show you up close are proprioceptors. All right. So here's our muscle, and you can kind of see this is our bicep. So we're going to zoom into it, right? And so here you can see here's a tendon, and then here's the actual muscle itself. Now, in the tendon, we're going to have what's known as a tendon organ. Basically, this is a bunch of sensory nerve endings, and that's sending information to the brain about basically how much pull is being put on that tendon. Because, it's not indestructible, so if you pull on it too much, you can imagine that tendon can tear. Maybe you guys have torn tendons, like in your ankle or something, right? So similarly, here's the actual proprioceptor. It's basically made up of what's known as a muscle spindle. Okay, these are slowly adapting receptors, and these nerves are going to wrap around specialized muscle fibers. So these muscle fibers are not there to generate force. Mostly they're there to kind of move along with the muscles, and then basically as these nerves are wrapping around them, and as those specialized muscle fibers, these intrafusal muscle fibers, are moving along with the actual skeletal muscle fibers, they then send that information to the brain. Okay? So basically what it's doing is measuring the muscle's length. Okay, that's what you see happening here. Hopefully that makes sense. So you have these, again, specialized little muscle cells, these intrafusal muscle fibers, not contributing to the force generated by your biceps. So you're curling the 25-pound barbell. These are not helping. They're simply there to give that information to your brain that, okay, we're stretching, we're contracting, stretching, contracting, right? We're not stretching too far, we're not contracting too much. That's all. Just measuring muscle length, as well as muscle movement, right? It's the other thing that proprioceptors do. So your brain also goes, oh, we're moving our muscles. Oh, okay, increase heart rate, increase breathing. All right. So with that, we have those proprioceptors, those little muscle cells, specialized muscle cells, embedded in all of our muscles, right? So, have you guys ever gone to the doctor? You're sitting with like your leg hanging over the bench, then he comes with that little triangular mallet and he whacks you just below your patella, and then your leg moves. Well, let's think about this for a second. So when he whacks you below the patella, what that does is it actually pulls on that tendon, and by pulling on that tendon, it pulls on this tendon, and it pulls on the muscle. So the muscle stretches. So those little receptors, those proprioceptors, are going to send that signal to the spinal cord as well as to the brain, saying like, whoa, we're being stretched. So its reaction is the exact opposite, right? So basically, all right, you're stretching me, whoa, I'm going to contract. Does that make sense? So if it's being stretched, if it's being pulled, it pulls back. So in other words, it contracts, and then your leg moves. Right? At the same time, you can kind of see there's several different connections it's making. Not only does the agonist have to contract, but the antagonist muscle has to relax in order to allow that movement to occur. Okay, we talked about that several lectures ago at this point. Okay, so again, let me just kind of hopefully say this one more time. Take the mallet, you hit the tendon, it pulls on the tendon, pulls on the tendon, pulls on the muscle. So the muscle's reaction to being stretched is to contract, to pull back, to prevent it from ripping, right? So it'll contract, and then the antagonist is going to relax to allow that to happen. And so your leg moves. Now, in the tendon reflex, it's a little bit of the opposite. So in this case, let's say you're sitting at whatever, the leg extension machine, right, at the gym. So you're using your quadriceps to move that little bar by your shin up, right? So you're kind of straightening out your leg if you're not familiar with that. So you're kind of in a seated position. Imagine simply extending your leg forward, right? So you're kicking out, right? Let's say you're using such a heavy weight across the shin that basically the muscle is at maximum contraction. It's really pulling on the tendon, and basically that tendon organ, that sensor that's in the tendon, monitoring how much it's being pulled on, is sending a signal to the brain and the spinal cord going, whoa, I'm being pulled way too much. I'm going to rip. So what it's going to do then is it sends an inhibitory signal back to your quadriceps saying, look, you're going to have to drop this weight, or otherwise I'm going to tear right off. And then it's going to send information, really, not so much the antagonist, I guess. In this case, since these are contracting, these are the agonist muscles. So that your hamstrings are going to contract to let your leg back down. Hopefully that makes sense. So I don't know if you guys have ever seen images, but sometimes weightlifters, they'll fight through the pain. So they'll be curling all sorts of crazy size barbells and dumbbells, and they're not paying attention to the pain. And these tendon organs, they're sending signals to the brain and they're fighting it. And what ends up happening is that the tendon right by the radius where the biceps inserts, it snaps. And so their muscle, the bicep actually ends up by their shoulder. And it's nasty. It's like the world's worst bruise. It's super painful. They have to have surgery to reconnect it. So you don't want to ignore that kind of pain, right? So basically, and that's what your body's trying to protect you from. It's trying to protect you from you lifting such a heavy weight and contract the muscles so hard that it rips it right off the bone. That's what the tendon reflex is trying to do. The flexor withdrawal reflexes, I think, is a little bit more intuitive to us. So this is in this image, hopefully you can see this. So here you are walking around minding your own business, you step on a tap. Okay, that sensory information goes up to your spinal cord, it'll of course go to your brain, and it goes to many different levels of the spinal cord because that the hamstrings are a very big muscle. So you get lots of stimulation going back down to the hamstring saying, whoa, pick your foot up off the ground, you just stepped on something. And in reality, you rarely just pick your foot up, right? There's a whole bunch of action that actually occurs, right? So yeah, more than one muscle group is activated to lift the foot off the tap. And then the crossed extensor reflex, I don't know how much you guys think about this, so it goes in concert with the withdrawal reflex. So let's just take a look at this image. So on this side, this image is what we just saw a second ago. You have stepped on the tack, it sends information up to the spinal cord telling your leg, hey, get your foot off that tack, to get your weight off of it. Well, if you lift one foot off the ground, you better balance your weight on the opposite foot, right? Like put that one down. So basically this is what the crossed extensor reflex does. So basically it sends information to muscles on the contralateral side, the opposite side, to, hey, you're going to have to compensate and hold up that person's body weight. Okay? So that's crossed extensors. So it's sending information across to the other side to compensate so you can actually, not fall down when you pick up your other foot. Hopefully that makes sense. All right, so we're going to take a look at a couple of other pathways. So far we talked about sensory information going up to the brain, right? We've talked about some motor information going down to our muscles, right? Remember the two different homunculus that we saw, the homunculi that we saw. We talked a little bit about our reflexes. Now there's just a couple of other pathways that are also important in the brain. Again, we'll just briefly talk about them, just so you have an idea of some other things that are out there. All right. So we had mentioned the basal ganglia when we talked about the brain. It's going to be a very important pathway. And again, remember, it's not just one brain region. It's several brain regions working together. And the importance here is that they're going to function initiating and terminating movements. And when you have damage here, you have a hard time doing that, like we see in Parkinson's disease. Okay, so you have these uncontrollable, abnormal body movements, right? So again, that's what that brain region does. And I just emphasize that because I don't know, a lot of you guys either work with the elderly or you're very familiar with Parkinson's disease. I mean, I think it's a fairly, I don't know, easy to I don't know. People, we all are aware of Parkinson's disease. So anyway, so I just like to use that as an example. Now the cerebellum, I think, is really cool in what it does, right? And I touched upon this when we talked about the brain, and I just want to kind of go back to this and talk about it in a little bit more detail. I think this is really neat. So I'll go through the bullet points, and then I'll try to explain this a little bit better. So basically what it's doing is it's going to monitor the intentions for movements from the cerebral cortex. Okay, you want to walk in a straight line. That is your intent. That is what your cerebral cortex, that is what you think you're telling your muscles, right? All right, so that information basically goes down to your muscles, and then basically as well as the cerebellum, and then the cerebellum is going to get feedback from the muscles, which basically say like, okay, I wanted to go straight. I am not so much going straight, right? So it'll monitor that and say, no, you may need to make this little adjustment. So it'll compare your intentions, walking straight, with the actual movements, and then it'll make corrections. Now, this is all occurring all the time. Okay, so basically what's happening is the end result is you have walked straight. Okay, if your cerebellum is impaired, like when if you've drank a lot of alcohol, you know how people who are drunk, they have very sloppy movements, right? They can't walk a straight line. That's like one of the classic things that, you know, police officers ask you to do when they ask you to step out of the car, right? Basically, what's happening is you want to walk straight. That is your intent, right? But alcohol has affected your cerebellum. So even though you tend to walk straight, the cerebellum's like, I can't help you. I can't monitor and give you correct feedback. So you're all over the place, right? So that's its job. And we can see exactly how important that is when it's not functioning right. You tip over, your movements are sloppy, right? Kind of, I don't know. I think it's kind of neat to think about how much that cerebellum actually does and how important its function is in movement. All right, so a few other pathways. Another pathway is something called the reticular activating system. Okay, so this reticular activating system is not just one brain region, it's actually many different brain regions working together. And basically what it's going to do is, well, wake you up, all right? So the more active it is, so the more active this reticular activating system is, the more awake you are, okay? So basically when it's activated, the cerebral cortex is activated, you're aroused, meaning not, you know, you're just aroused, you're awake, and then basically you are conscious, right? You wake up. Okay. So here are all the different brain regions that are involved in the reticular activating system. So again, once these brain regions are activated, they send information to many different areas of the cortex. So many different inputs can activate the system. So pain, light, noise, muscle activity, touch. Okay. You notice the sense that's missing? Smell, right? Smell is not going to activate the reticular activating system. Okay. It's one of the reasons why we have smoke detectors in the house or in our houses or wherever we are, right? Because the smell of smoke will not wake you up, right? So you have to have that fire alarm, smoke detector to wake you up. Okay, I mean, just think about all the other things that wake you up. Pain, like if someone just suddenly came in and socked you, you'd wake up, right? Or even think about it, like if you're drowsy or falling asleep and all of a sudden like someone just like whacked you, or if you've whacked your shin or something like that, like, whoa, okay, I'm awake now. Whoa, right, I'm awake. Or I don't know, you're falling asleep and your head hits the desk, it's like, whoo, okay, awake now. Light. Someone walks into the bedroom and turns the light on. You're like, ah, geez, it wakes you up, right? Pretty much immediately. Noise, that's how alarm clocks work. Muscle activity, right? So I don't know how aware of this you are, but let's say you're tired. If you just kind of do some little activity, like some jumping jacks, they say that jumping jacks wake you up as much as a cup of coffee does, right? So you might want to try that sometime if you're kind of falling asleep or trying to study. Getting up, walking around, having a little bit of muscle activity will actually wake you up. And touch, right? And we know that too. People walk in, they wake you up nice and gently, they'll touch you like, hey, wake up. You're like, no, 5 more minutes. Right? All right. We have our circadian rhythm of sleep, right? We had mentioned this before, right? Hypothalamus sets our circadian rhythm. We pretty much fall asleep at the same time, wake up at the same time, which, you know, is a good or bad thing. Like if you're used to waking up early in the morning and you got a day off, you still usually wake up early in the morning, right? Unless like you're really tired or, you know, went to bed super late or something, right? All right, we saw a little bit of brain waves when we talked about the brain. So, you know, hopefully, you know, you're seeing lots of activity in your cortex when you're awake. If you're not, we said that's pretty bad. That could be a sign of a traumatic brain injury. So sleep, right? It's really not clear what actually causes you to fall asleep. Like, what is it that takes you from consciousness to unconsciousness? One thought is that you have something called adenosine, okay? And your body's making adenosine all day long, and the levels are going to increase with the more brain activity, right? So it's not just like, I'm studying, I'm tired. although it might be a contributing factor. But the longer you're awake, the more brain activity there's been, the more adenosine has been produced, right? And these adenosine levels inhibit that reticular activating system. They're inhibiting the thing that's keeping you awake. Okay, so if they're impairing the thing that's keeping you awake, you're going to fall asleep. One of the ways that caffeine works is that it prevents that adenosine from inhibiting the reticular activating system. Okay, so it keeps that reticular activating system working longer. So you probably have heard of REM and non-REM sleep. So let's take a look at non-REM sleep first. So this is the non-rapid eye movement, and it has different stages. Okay, just said this. So again, during sleep, that reticular activating system is pretty much offline. The activity is very low. You can still, I suppose, if you have sensitive electrodes, you can still see it, but activity is very low because you're asleep. All right, so let's take a look at non-rapid eye movement sleep first. Right. So here we had seen these before. So when you're awake and you're thinking, you've got alpha waves. Right, we saw that. And then non-REM sleep, so again, non-REM sleep, we have stage 1, 2, 3, 4. And so you can see stage 1, you're drifting off with your eyes closed. This is something like you catch yourself, right? Dreaming or falling asleep. You're like, oh, no, I'm totally awake. This lecture is awesome. In stage 2, you're going to have dreams, some fragments of dreams. Your eyes may even roll side to side. However, it's not that rapid eye movement. It's not that major rolling of eyes side to side. Okay. Stage 3, you're relaxed. It's fairly deep sleep. They can actually, they hook up temperature sensors and blood pressure sensors to people, and your body temperature actually decreases. So does your blood pressure when you enter into stage 3 sleep. So they actually can see that. They don't have to look at an EKG. They can just look at your blood pressure and body temperature. And then stage 4 is deep sleep. Okay, and you can kind of see these are those delta waves you saw when we talked about the brain. Now here's the thing. In non-REM sleep, we're not going to have any kind of muscle paralysis, and we'll talk about that in a second. So in deep sleep, this is when people either wet the bed or they get up, they sleepwalk, right? They go raid the refrigerator. They don't remember anything about that because they're sleeping. It's just that their body is not paralyzed, so they get up and they do something. Sometimes they talk in their sleep. That's because they're in the stage 4. All right. Now, when we get to REM, right, most of our dreams are occurring in REM. Now, again, we just saw a slide ago. Not all of them, but most of them, right? So the way we get into REM sleep from non-REM is basically, as we hook people up, we can see that, machines that people go from stage 1 to stage 2 to stage 3 to stage 4 of non-REM sleep. Then actually, the brain patterns will shift back up to stage 2 of non-REM sleep, and then they'll suddenly go into REM sleep. So let's just kind of look at this again. And it kind of makes sense, right? You go from stage 1, where my little cursor goes, stage 1, 2, 3, 2, 3, 4, back up to 2, and then from this 2, you go into this REM sleep. Okay. And at that point, you'll cycle through this 1, 2, 3, 4 REM 2, 1, 2, 3, 4 REM 2, right? And you may not necessarily go back up to 1, but you'll go up to 2, 3, 4, 2 REM, 2, 3, 4, 2 REM, right? So until total REM sleep totals 90 to 120 minutes. Okay, and then your brain activity and oxygen use is going to be very high in REM sleep. Okay, and that again, that's when our dreams are. That's not too hard to imagine that's when our brains are most active. We're dreaming, sometimes really crazy dreams, right? So we're using up lots of oxygen, especially if you have anxiety dreams and stuff like that. Okay. One of the things that makes REM sleep important, and so you're not bedwetting, you are not sleepwalking during REM sleep. Okay. In REM sleep, you have what's known as REM atonia. REM atonia is muscle paralysis during REM sleep. Okay. So when you're in the REM stage, your brain will literally paralyze your muscles. Okay. Now, there's an interesting condition and I forget what it's actually called, but some people, all right, let me back up. Think about this. You're sleeping, you're in REM sleep. I'm going to kind of bring it back my picture because I kind of like telling stories when you can see my face. So anyway, you're sleeping, right? Okay, you're having a dream, you're in REM sleep, right? Something wakes you up. Now think about this. Your brain has to go from REM sleep, unconsciousness, but in this really fantastical world, to consciousness. You have to go from your body being paralyzed, right, in REM sleep, to suddenly not paralyzed and alert and responding to your environment. So you have to, click something off and click something on, right? So hopefully that makes sense. Now, in some individuals, it doesn't work that well. So they can go from REM sleep, they're unconscious paralyzed, to conscious, but they're still paralyzed. It takes a little bit for them to become unparalyzed. So they're totally conscious, fully conscious, but they're still paralyzed, right? And oftentimes, because again, remember, we've talked about this several times now, the brain goes, but I'm conscious, but I'm paralyzed, but I'm conscious, but I'm paralyzed. What's going on? It comes up with something crazy. And it's really interesting because across the cultures, across the world, the thing that the brain comes up with is that something is sitting on your chest. So this is what this image is. So this is sort of an image of that disease, and I'm forgetting the name right this very second. But basically, people wake up and they think there's like either a leprechaun, gremlin, I don't know, name your culture's kind of boogeyman sitting on their chest. It's never a happy thing. It usually comes with lots of anxiety and fear, right? Sitting on their chest until finally the brain can figure out, so sorry, let me click on non-paralysis. Let's get muscle movement back. And then once that comes back, it's like, oh, okay, got it. Conscious and moving. That's where I'm supposed to be. It's kind of wild, right? So again, brain doesn't always function too well. And sometimes, and for some people, this happens often, which is kind of scary. And some people, it doesn't happen often. It'll happen maybe once. It doesn't happen again for another 10 years. Maybe it only ever happens once. I've personally never had it happen. I've had people describe it to me, and they'll say like, yeah, it's like the weirdest thing. It was like a very panicky kind of feeling, and it felt like something was on my chest. Some people will say like, yeah, it looked like, it just seemed like, you almost like hallucinate that there's something there, because again, brain is trying to make sense of it. Other people say like, no, it didn't feel like, they didn't think that a thing was sitting on their chest, but it felt like a weight was on their chest. So kind of interesting, trying to get from that rematonia, from unconscious paralyzed, to conscious and moving. Sometimes things go wrong. Anyway, I wanted to share. Thought that was kind of interesting. All right. Any questions about that? If you do, again, as always, feel free to email me. I'm more than happy to answer questions, or feel free to ask in lab. All right. See you next time.